But without further ado, I have the great honor of presenting Dr. Hugo Cable from Psi Quantum. He was a postdoc of John's for 3 years before joining Psi Quantum, and he is going to tell us a bit about fusion-based quantum computing. Take it away.
Thank you. So I was John's postdoc for 3 years, and one thing I remember is he used to refer to me as Limey in reference to the British Navy. He also used to always tell me to speak up, so I hope my voice projection isn't as strong as I'd like to know, but I'll try and be clear. We're a startup. Psi Quantum is a startup based in California. We have a large architecture team that's devoted to finding the best ways to build a photonic quantum computer that's fault tolerant. And we have, in addition, an apps team and many engineering teams that are focused on R&D for components and systems engineering. And what I want to talk to you about today is our work on photonic switch networks, within the context of fusion-based quantum computing. So I'm going to start by providing some background. So what is FBQC? Well, so it's obviously a deep and well-defined piece of theoretical machinery, and if you're interested in the details, I refer you to this preprint publication. But in terms of why it's important, it provides a lot of simplifications when you are focused on developing fault-tolerant architectures, and it involves two primitives. So the two primitives are resource states, generally quite small, maybe tens of qubits typically. The key point being that they are constant size. So if we're running bigger instances of quantum algorithms, we don't need to generate larger states. We also don't need very many types of them. And our other primitive is fusion operations, which are destructive, entangling projections. So I'm sure most people in the audience are familiar with, very familiar with quantum computing theory, but for those who aren't, in terms of these graphs, this is an example of a 6-qubit ring. So the edges represent bipartite entanglement, and the nodes represent qubits. It doesn't have to be defined by photons, right? These could be ions. They could be the ground states of ions. It could be superconducting states. In terms of the fusions, they're destructive 2-qubit gates measurements. A very natural example would be a probabilistic Bell state projection. In cases where it works, it will perhaps give you 2 bits of classical information. For those familiar with stabilizer language, for example, you'll get a parity bit for an XX and a ZZ. And in cases where they succeed, the measurement will give you a larger correlated qubit state. This is an abstract representation. Switch networks are important because they tell us physically how to lay out these states in space and time. But before I proceed, I should point out that there's a bit more to switching. And in some sense, they are a fundamental requirement for linear optical quantum computation. And so, one very famous point of reference, which has come up already a few times in the last couple of days, is boson sampling. This is a model of quantum computation that has most of the same elements as a universal photonic quantum computer. So it has single photon sources, which are in some sense highly non-classical. It has a passive linear optical network, and it has single photon projection measurements. And we know that the problem of sampling output photon statistics is a computationally hard problem. But yes, it's not believed that boson sampling is equivalent to universal quantum computation. So there is a fundamental requirement for switching, which is a challenge because it's a difficult technology. And there's a long history of trying to get rid of the switches in linear optical quantum computing. So one example of a way to do this is that was written by myself and colleagues is something that we call relative multiplexing, right? So if you have qubit states and you want to merge them at some circuit, a naive way to do it would be to multiplex both sides to bring your qubits together in space and time. But that's doing too much work, right? Generally what you need to do is you just need to catch up one state with another, rather than trying to synchronize things to very specific points in time. Another idea that gained a lot of traction was applying ideas from percolation theory that are familiar from pure maths and condensed matter physics. Up here I have a picture of a random grid graph, and the edges are generated probabilistically. I guess would represent bipartite entanglement generation, and the vertices represent qubits. And the point is that when you generate a random graph like that, we know that it exhibits threshold behavior. So if the probability for creating edges is above a certain threshold, then we guarantee, with probability tending to 1, that we'll get spanning path of entanglement somewhere across this grid. So to complete this background, so fusion-based quantum computing is defined on these primitives by what we call fusion networks. So we imagine that we have some resource states and some particular arrangement of fusion operations on them, and this arrangement will generate you a three-dimensional sort of cluster state that embeds like fault-tolerant protection, and the key ideas is that it very naturally incorporates the probabilistic nature of the circuits that we have in linear optics. And you can show even simple examples of fusion networks, such as with the 6 ring, can reproduce famous standard results like the performance of a surface code in a more traditional measurement-based paradigm. So why photons? Well, in order to make a useful quantum computer, our contention is that it needs to be fault tolerant. If it needs to be fault tolerant, it needs to be large. We need to be able to create millions of physical qubits, and we need to be able to do billions of gates. And photonics provides a convincing route to implementing that in practice. So one aspect is in terms of circuits. We can implement waveguide circuits that are amenable to mass manufacture. We've partnered with Global Foundries. It's a tier 1 foundry. Another advantage of photonic qubits is that they're free of many of the noise and decoherence issues that affect matter-based qubits, trapped ions and so on. And another key advantage is that photonics typically is fast, right? It's no surprise to have photonic hardware running at gigahertz type speeds, which is orders of magnitude faster than typical timescales for superconducting qubits and cold atom systems. And then another reason why photonics is very promising It's because we know that we have relaxed cryogenic requirements. So our main cryogenic requirement is the single photon projection, for which we'll use superconducting nanowire detectors. And these, operate at a few kelvins. So, we avoid problems of millikelvin cooling and dilution refrigeration and so on. And our CEO, Jeremy O'Brien, has given some great talks and a great overview on our general approach. And I refer you to our webpage where many of these talks are linked. So, I'm going to review the circuits. We work with dual rail qubits. A qubit in our system will be defined by a single photon that's in one of two waveguides. We can also encode a qubit in time, in which case the 0 and 1 logical states are defined by the time bin in which the photon is located. One advantage of a dual rail qubit is that it's sort of a naturally fault tolerant encoding. But if you don't measure anything, then it's not there. In terms of sources, we imagine spontaneous four-wave mixing or parametric down conversion. Important thing to appreciate is that it's a random process for generating single photons. You produce pairs of photons, and you have a signal photon when you herald a photon in the other arm. Typical success probability will be 1 to 5%. And then our circuits, as I mentioned before, are waveguide circuits, and our entangling operations, they're all probabilistic. And I'll say a bit more about that. And finally, we get to the switches. So, a switch for me is a black box. It does optical routing. It does some form of permutation on the inputs. But conditioned on information about what's happened previously. So, we have some high-speed electronics that's implementing feed-forward logic, knows the history of the states before they get to the switch, and configures the switch box appropriately. Now, switching is a difficult problem, right? Our switches need to be compatible with cryogenic operation. They need to be fast. We need to be talking nanoseconds, not milliseconds or microseconds. So that excludes options like MEM switches, for example. And it points you to the need to develop an electro-optic switch. There's various options for this. There's switching based on the Kerr effect, or carrier injection depletion, or the Popples effect, and other candidates. Because fault tolerance has very demanding requirements on errors, we also have very tight specs on losses, on extinction ratio, on phase errors, i.e. voltage accuracy. But I'm not going to talk about the hardware anymore. I'm going to talk instead about schemes and circuits for switching. And so it's good to stand back and just review where in the architecture we need switching. Well, most of the switching that we're going to need is going to be in resource state generation. And that's because our photon sources are probabilistic. Even in theory, they can never be more than 25% successful. Typical numbers will be 1 to 5%. In order to make small 2-qubit states, the standard circuit, which takes 4 input photons and outputs a 2-photon Bell state, succeeds with probability less than a quarter. If you want to generate a 3-qubit entangled state from 6 input photons, that works about 3 in 32 of the time. And our fusion measurements, they work 50% of the time, ideally. And then also we're going to have, fusions at the end, final fusions that will stitch together our resource states. And by choosing the basis in which this is done, we can implement logical operations and implement algorithms. And this kind of switching can be incorporated in the multiplexing that we need anyway to boost the success probabilities up to useful values. So, in terms of thinking about like the most efficient way to do switching, this is the area where my efforts were focused at PsyQuantum. It was actually surprising that not that much work had been done, beyond N-to-1, multiplexing circuits. And we've come up with a bunch of results that we published last year. We have a bunch of useful techniques that we'd like to share. So, one observation is that if you look at the typical tasks that you need to do in our stack, it turns out that you can pretty much do them with black box switches that are switch depth 1 to 2. This is important because we need to minimize the loss of photons C in their lifetime, and we still expect switching to be our lossiest component. There's also many techniques to combine different functionalities within one switch network. So, an example of that would be I have probabilistic inputs and I want to multiplex them, but I also want to have a corrective swap. And if you look carefully at the operations that you get in switch networks, you can often combine things. We've also, written down like optimal schemes. So a typical task would be, multiplexing groups of 4 photons for a Bell state generator. And we have a lot of schemes that are sort of novel forms of time multiplexing. And I'm going to explain, why time multiplexing is so powerful and should be thought differently in the context of an architecture rather than just multiplexing single photons. So this is what the switching black boxes look like initially. So our simplest example will be a 2x2 Mach-Zehnder interferometer, which I'm sure is highly familiar to many people in the audience. So this is like a circuit notation which represents a 50-50 beam splitter. This is my active phase shifter. If we set the voltage so we get a 0 or pi phase difference between the two arms, then we select identity or swap as the functional operations. Sometimes it is so important to minimize the depth of switching. We sometimes think about fractions of a switch. So a different implementation of an MZI will be a push-pull where we have 2 half-length phase shifters in both arms with swing pi over 2. And by alternating the one that's on, we can get a swing of pi between the arms in a different way. So, if we take our Mach-Zehnder interferometers and we want to make a big N-to-1 mux multiplexing network, like a very standard way to do this would be to pick one of these switch fabrics that you can find in the literature. So in this example, I'm multiplexing 16 sources. Let's say we want to multiplex 16 sources so we can boost an initial success rate of 1 to 5% to 15 to 50%. Then we could use a log tree, or we could use a chain, or we could use a cavity where we can switch out from our storage after a fixed number of steps. Another way that we can do this is with a generalized Mach-Zehnder interferometer. So these are known in the literature, but much less used than vanilla Mach-Zehnder interferometers. My 50-50 beam splitter has now been generalized to a big N by N Hadamard that does equal power splitting. And I have one layer of phase shifters that can give me either a 0 or pi phase shift in each arm. And you know, we found a bunch of optimizations for these constructions. So, for example, you know, you might ask, you know, how short can I make these switches and still produce a useful switching black box? So, for example, if we limit the range of these things to pi over 2, the best you can do is flip the switch between two configurations. If it's 2/3 of pi, you know, you can make a 3x3 switch, or you can make a 4-to-1 switch in a 6-mode network. So that we've got some like various nice mathematical results like that. But in terms of making composite networks, you know, a key point is like a generalized Max-Ender interferometer on n nodes will not allow you to do arbitrary operations. So in principle, you know, you'd like to do n factorial operations on your input, so you can arbitrarily rearrange. In fact, you only get n, and they could be like a family of swaps, or it could be a set of, you know, cyclic permutations. But with this, in some sense, with a bit of additional, is actually really sufficient for your needs. And so this example is called rastering, and it's a kind of form of time multiplexing. And the way it works is, you know, you can consider that I have a bunch of inputs here. So here are some input time bins, space time bins. Some are occupied, some are not. So one thing I can do, right, these inputs, these photons are going to be in fibers. I can happily diddle the delays and stagger the time at which the inputs get into my switch network. And then what I can do, because I know that the GMZI will allow me to route one specific input to one specific output, I can do an arbitrary rearrangement of these inputs in time. So I can keep pushing these inputs into this delay network and reorder them as I'd like. And then at the output, I can restack these states. So in a sense, you know, they're nicely organized into space-time bins, lined up, you know, similar to the way they came in. So, you know, this is a very nice time multiplexing idea. You know, you'll already have, if you imagine like a full stack, you know, you're already going to have muxes. So it's very cheap to add, you know, staggering of delays and sequencing of operations. You know, if you look in the literature at a more kind of standard way of doing these things, you know, you'll find, for example, a spanker network, which takes a different approach to this. You know, it assigns every input and every output to a GMZI, and that has a massive network of crossings between them. But, you know, our priority is to save loss and to make things compact and efficient. This is obviously not optimal for our application. You know, another example would be like concatenations of many switch networks or crossbar topologies that are used for MEMS and NEM switches. So I have 10 minutes left, 5 minutes. Okay, so before I go to some more detailed examples, I'll just, you know, quickly, you know, go over some of the key applications. So, you know, we'd like to turn our n-to-1 muxes into n-to-4 muxes or n-to-6 muxes because, you know, we need to populate the inputs of a Bell state generator or a GHZ generator. And, you know, another application of this, you know, rastering time multiplexing is very useful here. So, like, you know, there have been many, you know, very impressive experiments in the last 10, 15 years of you know, single photon multiplexers. But the, you know, the naive thing to do would be to take, you know, one of these experiments and then turn it and say, okay, I have a way of multiplexing 4 photons into a Bell state generator. A simpler thing to do is just to take an n-to-1 switch network and in turn feed 4 different outputs and compensate the delays at the output, which is something that comes for free. So time multiplexing like this needs only one layer of switching. It doesn't need 2+ layers of switching, which is what the default is. Time multiplexing is also very, very powerful downstream at the point at which you make logical qubits. So this is it's a highly technical scheme, and I refer you for the details to this publication. But essentially, you can think about it as building up a logical qubit from 1,000 physical qubits, whatever. But it's a form of maybe 3D printing is a good analogy. We're sort of rastering the generation of this logical qubit. And the important point is the time multiplexing can be done in a way that's compatible with the fault-tolerant fault-tolerant operations that you need to do. Another application is optimal multiplexing networks. So if you look at an N-to-1 single photon multiplexing circuit, and you say like I want to multiplex 4 photons for a Bell state, if I were to use these permutations that a GM_I gives you, like how efficient can I be? Well, mathematically, the most efficient you can ever be is equivalent to a saving in footprint of a half if you have one output circuit. So here's one way of doing this. So I've got my 4 N-to-1 muxes, and I supplemented it with 2 layers of MZIs. And if I'm very careful and I look at all the patterns of inputs, and I label things, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, you can show that it's always possible to set the switches to allocate 1 photon to 1, 1 to 2, 1 to 3, 1 to 4 without conflict. And we've also written down a similar optimal scheme for multiplexing groups of 6 photons. If you go further and you have like what I call a photon sharing scheme, where we try to feed a number of circuits simultaneously, we can save even more in terms of footprint. We can save up to a factor of like 3. This is a scheme that we have for doing this. 2 layers of GM_Is. Our first layer of GM_Is allows us, so the grey squares here represent all the inputs. They will be probabilistically occupied at the beginning. Our first layer of GM_Is allow us to push across the columns, and the second layer across the rows. And you can write down a simple algorithm to try and populate all these outputs. Such a thing is very close to the optimal efficiency you can ever achieve. Do I have time for one more example? Another observation is that these switching boxes, as I've presented them so far, they're very, very classical objects that do permutations. But there are some more interesting things that you can do. So one thing, if you take a GM_I and you do half settings, you can sort of make your GM_I behave like a reconfigurable beam splitter, where you can kind of fix sets of inputs and output ports. This is kind of interesting because if we put a single photon into a beam splitter, in some sense it does something non-classical, right? It gives you a superposition. And so one way that you could apply this, for example, is to create a superposition of your single photons as your output qubits, while also putting them into your measurement circuit. So this provides you a way of creating time-encoded qubits without having to have a separate stage of space to time encoding. And in this final example, I'm going to go back to the theme at the beginning, which is that I mentioned that we'd like to get rid of switches as far as possible. So one thing that we've done is written down generalized families of Bell state generators. These are, instead of having the usual 8-mode device, these are 16 or 32 or 64. And you can imagine that probabilistically, sources will give you 4 or 5 or 6 photons. And if we don't have any switching at the input, it turns out that we can still have an effective scheme. We lose a factor of about 3 in footprint. But it's still an effective way to generate Bell states. The only question for quantum computing is like how clean are the outputs, right? Because you can't throw out sources which herald you a vacuum, but actually the vacuum that it heralds is not perfect. And yeah, is it okay to go to the front? So just as to commemorate John, I thought it'd be nice to recite this poem about Lord Ernest Rutherford. So let me tell you the tale of Lord Ernest Rutherford, whose scattering formula is widely admired. He fired off cannonballs at pieces of tissue, which bounced right back at him, clouding the issue. His graduate student, Hans Geiger, works in the lab like a tiger, and received only credit for his namesake, the counter, from Lord Ernest, the bounder. Lordy was smug to the end of his days by the fact that quantum mechanical effects didn't phase the truth of his wonderful scattering formula. Buola, 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 buola. But there's a rumour that in fact it was really derived by a barmaid he met on London's east side. He did the derivation when he promised to elope on the back of a tattery envelope.
Do we have any questions for Dr. Hugo Cable?
Thank you very much for the talk and poem. So I was wondering if you use these 6 rings in your as your building block. Do you have like a simple physical intuition for why that's the right way to go about it?
Well, I mean, the point is that it's a flexible network, so you can consider any number of resource states and configurations. I believe, if I'm not wrong, the 6 ring is a simple way to reproduce the surface code results, or so you do at least as well.
So you can go into 3 dimensions, is that
Yeah.
why you have 6, and then you can sort of have 1 to spare for each?
Exactly.
Yeah, okay. Yeah. Thanks.
Question about the time scale for operations. You mentioned nanosecond time scales. Are you primarily limited by the dead time of the detectors or by the coherence time of the sources?
Well, I mean, ultimately, your time limit is how quickly you can generate the photons and therefore length of the photons, right? I mean, one of the interesting things about switch networks is that you can configure things to work around slower components. Maybe at some cost and efficiency. To some extent, you're also limited by the rise time of switches, because obviously you need your switches to settle between events. That's a limitation. Like the only thing you can do is create things in batches and switch between batches of events. Yeah. So I think it's kind of fortunate that the timescales for components typically kind of line up. When there's differences of a factor of 10 or something, you can work around it.
Can you say what sort of coherence times you're working with?
Well, for photons, right? It's the time for the photons to propagate through the sources, through all the resource state generation onto the detectors. It's not hundreds of nanoseconds that you need.
Thank you.
Are there any further questions? Yes.
Okay. If fusion fails, then it is just you lose 2 qubits?
Well, there's different ways a fusion can fail. So one of the important things about FPQC is it builds in the failure modes in a way that's quite efficient. So, in some cases of failure, you'll get 1 bit of information instead of 2. Sometimes you'll get no bit of information. But, for us, it's a type of erasure.
Erasure.
All right, well, if there are no further questions, let's please thank our speaker again.